first chapter of standard 10th ICSC. That's your chapter force. Now what is force? We have been learning about the word force, which is a physical quantity, for a very long time. Since class 6th, 7th we have been learning what is force. Force is either a push or a pull activity, isn't it? So to apply myself to something, to apply my force to something, either I can pull the object or I can push the object, and that can lead to a certain things. It can lead to a change in the state of motion. That means if a body is moving towards me, if I push it, I can stop the body, or at least I can reduce the force with which the body is coming towards me. Correct? I can also bring it to rest. If there is a stationary ball in my hand and if I push it, what can happen? I can change its state again. I can change its state from stationary to motion. What if I squeeze a lemon? If I squeeze a lemon, I change its shape. And what if I hit a ball with a bat? I can change its direction. So force is such a physical quantity which can, not always does it change, but it tries, it can. So it changes or it tends to change. So why is this word very important? Why is this sentence important? Because force may or may not bring about a change. Even if I am applying a lot of force, I won't be able to move a wall. But I am applying the force that is needed. So that's why it is very important to know for force that force may or may not bring about any visible change. But force is such a physical quantity which tries to change. So it changes or it tends to change the state of rest or motion, or it can change the shape or the direction of any object. So that's what we understand about force. So far that's what we know about force, that it's a push or pull activity which changes or tends to change the state of rest or motion, the direction or the shape of an object. Now force is actually something we derive from momentum. What is momentum? Now these are all your older concepts, but we need to apply them all the time. So I am just doing a quick recap. So what is momentum? Momentum of any body is the product, that is the multiplication of its mass with its velocity. So if you're talking about any object A, so if its velocity is v and if its mass is m, what will be the momentum? Momentum is denoted by small p. So we are talking about linear momentum, which is a body which is moving in a straight line. So linear momentum is denoted by the letter p, small p. So small p is the product of m and v. So small p is going to be mv. What would you understand by change in momentum? How do we denote change? We denote change with delta. Delta. We use the word, the symbol delta. So delta P will be delta mv, because P is equal to mv. So delta P should be equal to delta mv. But since we are talking about a single object, the mass of the object does not change really. It does change in some cases, but let us take the mass of the object to be constant because we are talking about the same object A, correct? So if the mass of the body is constant and if momentum is changing, so what will be delta P? Delta P will be m into delta V, because mass is not changing. So the momentum or the linear momentum only changes because of the change in velocity. Is that right? So delta P, that is change in momentum, is equal to mass into delta V. Is that correct? Alright. Now, the most important question is, why will the velocity change? Isn't it a change in the state of motion? Change in velocity, increase in speed or decrease in speed, increase in velocity or decrease in velocity? What can cause it? What is the only thing that can cause it? Yes, it is force. Force is the thing that can cause a change in velocity. If you withdraw force, velocity can decrease. If you increase force, velocity can increase. Correct? So force is the reason why the velocity of the object is going to change. So coming back to our momentum, Delta P, linear momentum or change in linear momentum, is the product of mass and change in velocity, which is caused by force. Alright, this much is clear? Alright, what is rate of change of momentum? Rate of change of momentum, rate of change of anything is with respect to time. So rate of change of momentum is delta P upon T, isn't it? Everything divided by time means rate of change. So delta P by T is going to be M delta V by T, isn't it? M delta V upon T, because P was M, delta P was M delta V. So M delta V upon T. What is delta V and what is T? Delta V is change in velocity. What is T? T is time. What is delta V upon T? Think about it. Change in velocity upon time, or rate of change of velocity. What does it mean? Rate of change of velocity is nothing but acceleration. So what is the rate of change in momentum? That is delta P upon T. That is equal to mass into acceleration. That is because delta V upon T is acceleration. And why is all this changing? Why is the velocity changing? Because of force. So what causes the rate of change of momentum? It's force. That's why force is equal to mass into acceleration, because momentum or linear momentum is equal to mass into velocity. Is that clear? That should be clear. We have learned this in our standard 9th already. Even 8th, 9th, we have been studying this. We have compared momentum and force many times. Now, talking about the units of force. What could be the SI unit of force? Force is a product of mass and acceleration. What is the SI unit of mass? Kg. What is the SI unit of acceleration? Meter per second square. So what is going to be the unit of force? SI unit of force? Kg meter per second square. What will be the CGS unit of force? Gram centimeter per second square. So kg meter per second square is given a name based on a scientist, Newton. So the unit of force is said to be Newton, which is in fundamental units, it is kg meter per second square. And in CGS unit, it is said to be dyne. So what is dyne in fundamental units? Gram centimeter per second square. Is that very clear? So this was your previous year's concept. Now let us begin with our chapter force. Now we have to understand a few concepts to understand this chapter better. The first thing we have to understand is the axis of rotation. Now what is the axis of rotation? Let us try to understand. If I have a ball in hand and if I apply some force on it, so it will move straight. It will move on the, it's a free ball. It can move straight, it can spin. So it is undergoing translational motion, that is in a straight line. We also call it rectilinear motion, and it is also undergoing rotational motion. So it is rotating. What does it mean to rotate? It rotates about a fixed axis. There is an axis about which it will rotate. So axis of rotation is a fixed point about which a circular object can rotate. Can I say that? Now let us talk about another fixed point which we call as a pivot or a fulcrum. Pivot or a fulcrum are those points about which an object is going to move. Now how it moves, let's talk about that a little later. But why are we introducing a pivot? Because whenever a pivot is introduced, we are restricting the translational motion of that object. What does this mean? Let me repeat myself. When I take the same ball, the free ball that we had in hand, which I had applied some push force to, the one that we spoke about. So now I am taking this ball and I am fixing it about an axis of rotation. Now if I apply the same force on the ball, what is going to happen to the ball? It will not be able to go ahead because it is fixed in an axis, and now it is only going to spin. It is going to have pure rotational motion. So the moment we restrict the position of the ball or we restrict the translational motion, different type of motion comes into the picture. And that type of motion is what we are going to be studying in great detail in this chapter. So the type of motion that we see in an object, the type of motion that is caused by a force, by a regular force on an object which is fixed about a point, or which is fixed about an axis, is causing a different type of motion, and this motion is identified by a term called as moment of force. That means the force which is applied on this body is not going to cause a straight or a linear or a translational motion. It will cause a rotational motion of some kind. So if you take beam balance, for example, what happens? If you take a beam and it is fixed about the center, so if I put weight on one side, on the right hand side, the beam will move like this. If I put weight on this side, the beam will move like this. So the motion is not a straight line. It is either moving clockwise or anti-clockwise, isn't it? So this type of motion is of a rotational motion, can we say that? So this type of motion which is caused by a force on a body which is moving about a fixed point. One point is fixed. That type of restricted motion is caused by the moment of force. This moment of force is also identified by another term which we call as torque. Moment of force is basically force तो हमने उतना ही लगाया है in the same manner. We are not changing how we apply the force, but because the body is fixed about a point, fixed about an axis, that means fixed about a fulcrum, pivot or an axis. If you fix any body about any point or any line, it will not have pure translational motion, it will have a moment, and that is called as moment of force. That is also called as torque. Now what are the things that this moment of force is going to depend on? Moment of force is going to depend on how much force I apply. So the more the force that I apply on a body which is fixed about a point, more force that I apply on a body which is fixed about a point, more moment it is going to see. That means it is going to go clockwise or anti-clockwise with more vigor. Can I say that? Okay. What if I increase the distance from the fixed point? If I keep increasing the distance from the fixed point, again the moment increases. And the best example of this is, why is the handle of the door at the rear end, completely extreme end of the fixed point of the door? Why, if the door is fixed over here, why is the handle so far away from it? Why is it at the other end? Because more the distance from the fixed point or the pivot or the fulcrum, these three names would mean the same thing to you. More the distance from the fixed point, more the moment of force. So what are the two things that moment of force or torque depend on? It depends on, obviously, the amount of force that you apply on the body, isn't it? And it will also depend on the distance from the fixed point. And moment of force or torque is symbolically it is represented by the letter T, tau. It's not exactly T, it's a Greek alphabet, tau. And this is equal to the force into the perpendicular distance from the fixed point. Remember, the perpendicular distance is always going to be from the pivot or the fulcrum or the fixed point. So what is tau equal to? T, or moment of force, is equal to the product of force into the perpendicular distance from the fixed point. So what will be the unit? The unit of torque or the unit of moment of force is equal to the unit of force into the unit of distance, that is Newton meter. So like I said, the moment or the movement about a fixed point can be clockwise or anti-clockwise, isn't it? Doesn't this tell us that this is a vector quantity? Because direction to head, if there is magnitude, which is the product of how much force I have applied and how much distance the force is applied from the pivot, it has a magnitude and it also has a direction because it is either clockwise or it is anti-clockwise. So obviously it has a direction. So if it has magnitude as well as direction, what type of quantity is moment of force or torque? Yes, it is a vector quantity. Direction is very important and it will be very important for you for numericals and all the problems that you will be attempting. Now we are going to talk about a concept called equilibria or equilibrium. We also know this word. What does equilibria or equilibrium mean? Equilibrium means a state of rest or a state where we don't see any visible change. So that equilibria can be of two types. It can be static, it can be dynamic. For example, there is a book that is resting on a desk. What happens? Let us see. So firstly, the book is going to exert some force on the bench. The bench is going to exert a reaction force on the book. And this action and reaction, remember Newton's third law of motion. Remember, action and reaction does not occur on the same body. So action is performed by the book on the table. Reaction comes from the table to the book. They are of the same magnitude and of opposite directions. So when the weight of the book is equal to the reaction force that the table exerts upwards, then the book is static, the book is not moving. What if I keep adding more and more and more and more and more books? At a point the table is going to give away that okay, that's all the weight that I can take. So now the weight of the books that are acting downward is much greater than the reaction force that the table can give upwards. So the table will break. So that situation, the body is not in equilibrium. However, as long as the action and the reaction are of equal magnitude but in opposite directions, then we can say that the body is in static equilibrium, isn't it? So if you take the best example is the book. There is another very good example, the example of a beam balance. Beam balance is used for measuring different things. Correct? They are used by vegetable vendors. So what is the concept of beam balance? In a beam balance, you put some weights on one side. So let's say if I put some vegetables on one side, on the other side I put some weights. So vegetables and the beam balance is again, remember, pivoted at the center. Don't forget that. So the vegetables are going to cause some kind of a motion, some kind of a moment of force, and the weights are also going to cause some kind of moment of force, and these two moments will at a point balance each other. When will they balance each other? When they are at equal distances and when the forces, what is a force here? The weights that we are using and the weight of the vegetable, when both the weights are same, both of them are going to cause the same moment of force in the opposite direction and they will come to a balance point or they will come to a static equilibrium. Alright. Now what about dynamic equilibrium? Dynamic equilibrium is a situation where, for example, the body is in motion. The body is not static. The body is moving, but it is moving with the same velocity at the same height from the ground. So if we take an example of a car moving at the velocity of, let's say, 20 meters per second. If a car is moving with a constant velocity v of 20 meters per second, what does it mean? So for this car, the friction that is offered by the air is same as the force with which it is moving. That's why the velocity is not changing. So here what is happening is the air resistance and the friction that is offered by the air on the car matches the dragging force. We call it the dragging force which is offered by the fuel. If both the forces, the force with which we are going ahead and the force with which the air resistance is acting, if they match, so the car will continue to move in the same velocity, isn't it? And when we talk about aircrafts, what happens? The thrust or the force with which it moves ahead is same as force with which the air resistance works in the opposite direction, then it will continue to move with the same velocity, no change in velocity, because aage ka force, piche ka force, both are same. And why is it floating? It is floating because the weight of the flight, the weight of the aircraft is matching the weight of the buoyancy which is offered by the air around it, by the atmosphere around it. So when the buoyancy matches the weight of the aircraft and the thrust matches the air resistance of the aircraft, it is moving with a constant velocity. Velocity change hona matlab force apply hua hai. Velocity is constant. So when velocity is constant, that can mean that all the forces acting on the body cancel out each other. So they are moving with the constant velocity when you take the example of a car or an aeroplane moving at a constant velocity. So these are your examples of dynamic equilibrium. Remember, static equilibrium, body is in a state of rest. Dynamic equilibrium, body is in a state of constant velocity. Now, if we talk about equilibrium of bodies moving in circular motion, now it's very important to know the difference between rotational motion that happens about a fixed axis. The body moves around a fixed axis, and circular motion where the body moves around a point, the whole body moves around an external point. So when a body spins, it is a rotational motion, and when a body revolves, it's not rotating anymore, it is doing revolution. Revolution happens around an external point. So that is called as a circular motion. Here the whole body moves around this imaginary point which is outside the body. In circular motion, you also get to see equilibrium. For example, electrons revolving around the nucleus. How does it revolve around the nucleus? Because of the balance of forces. The balance of forces are offered by the attractive forces of the nucleus, because nucleus is positive, electrons are negative, and the repulsive forces of the other electrons around this electron. There is not one single electron on the orbit. There can be many more. So the repulsion between the electrons and the attraction between electrons and protons, or electrons and nucleus, that balance allows the electron to keep spinning at a fixed speed, can we say? At a fixed speed, because velocity is not the same, direction is changing. So let's say it is moving around a fixed speed without spending any extra energy or without applying any extra force. This balance of the attraction and the repulsion allows it to move about the center, which is the nucleus. We can talk about planets, obviously. Earth revolving around the sun in an elliptical orbit. How does the Earth move around the sun? Because Earth is having some kind of attractive forces. What type of attractive forces with the sun? The Earth is going to have gravitational pull on the sun. Earth is going to have gravitational pull on the moon as well, correct? So this balance of centripetal and centrifugal force, we are going to come back to that in the end of the chapter. So the centripetal force which acts towards the center and the centrifugal force which acts away from the center, they balance or cut each other out, and the Earth can spin in its orbit around the sun without spending any extra energy or without applying any extra force. So these are also your example of dynamic equilibrium. Now we are going to talk about the conditions for which a body is said to be in equilibrium. The conditions for which a body should be in equilibrium. सबसे understandable condition क्या है? If all the forces acting on a body results to zero. So if the force acting from this side is equal to the force acting from this side, there is no movement. If the force acting downwards by the book is same as the force acting upwards, which is offered by the table, then there is no movement. And that means the body is in equilibrium, isn't it? So when you are looking at any shaped body, the sum of all this is a vector sum. Because force is a vector quantity, so you can't just add all the forces. You have to do a vector sum. We still haven't learned vector algebra, but you should be able to write this. The vector sum of all the forces, or you can simply say the net of all the forces. The net means the vector sum of all the forces should be equal to 0. That means if there are three forces F1, F2, F3 acting on any shaped body, and if their vector sum or their net activity or their net effect comes to 0, the body will remain as it is. It will not change its shape, size, motion, direction, nothing. It is in a state of rest, or it is in a state of equilibrium. Alright? Forces are acting, but it is in a state of equilibrium. What is the other thing that can lead to a state of equilibrium? We have now learned about moment. What is moment? Moment is the product of the force acting on a body and the perpendicular distance from the fixed point or the pivot, isn't it? So if I say the algebraic sum of all the moments, the algebraic sum of all the moments that are acting on a body, matlab if there are 4 or 3 forces acting on a body, so we take the distance of the one force from its pivot, then we take the distance of other force from its pivot and multiply it, then we take the third force and we multiply it with the distance from the pivot, then we check which of the forces is causing anti-clockwise moment, which of the forces is causing clockwise moment, then we add them all. Now how do we do an algebraic addition? To do an algebraic addition, we need to take a sign convention. And what is the sign convention? Remember this, anti-clockwise is always positive, clockwise is always negative. Let us look at this example and understand what I am trying to say. Now here we have a body which resembles something like a seesaw, and there is a mass, there is a weight, actually not a mass, the weight of 150 Newton which is acting on the right hand side of the pivot, that's the fixed point, and there are two weights which are acting on the left hand side of the pivot, and both the weights are of 50 Newton each. Weight is same as force, remember this. Mass is not same as force, but weight is same as force, isn't it? Always remember that always we are trying to go towards the pivot. So this 150 Newton weight is going to go towards the pivot. So when it goes towards the pivot, what is the type of motion that it's going to cause? Clockwise motion. And that is going to be negative. What is the distance of this 150 Newton from the pivot? The distance is 1 meter. So what is going to be the moment about this pivot which is caused by the 150 Newton weight? Yes, it is going to be minus 150 into 1 Newton meter, isn't it? Because it is the product, moment is always the product of force that is given in Newton and the distance from the fixed point, which is the pivot in this case. Now let us look at the other two weights which are present on the left hand side of the fixed point or the pivot or the seesaw. Alright. So now the first weight is of 50 Newton. It is at a distance of 1 meter and it is going to go towards the pivot. When it goes towards the pivot, it is going to cause a anti-clockwise moment which is positive. So that will be 50 into 1, force into perpendicular distance from the pivot, and it will be plus. So it will be 50 Newton meter. And what about the second one, which is the farthest? It will be 50 into 2 because it is at a distance of 2 meters from the fixed point. So it will be 100 Newton meter. Again, it is trying to go towards the pivot. So when it goes towards the pivot, what happens? The motion is anti-clockwise, and anti-clockwise motion means positive. So two forces are causing anti-clockwise moment. One moment is due to the first 50 Newton body. It is going to be 50 Newton meter positive, and for the second one it is going to be 100 Newton meter positive. So what is the net force acting in this seesaw situation? Minus 150 Newton meter clockwise and 50 plus 100, that is for both the bodies, anti-clockwise, so they are positive. So minus 150 plus 50 plus 100 becomes 0. So the algebraic sum means with correct convention, with the correct sign, the algebraic sum of all the moments about the fixed point is 0. So this body is also in equilibrium. It's in a state of static equilibrium.
So children, it is very, very important to note one thing about clockwise and anti-clockwise motion, that when I'm demonstrating it on the board in front of you, I am showing clockwise motion as it appears to me and not how it appears to you. So my clockwise is something that appears to me that might appear anti-clockwise to you. So when you are looking at something and the body is going through a certain motion, the moment if it is caused in a motion which is along the clock, it is called as clockwise motion, and the moment which happens against the clock's run, it is called as anti-clockwise motion. So always try to see that the body that is in front of you, what kind of motion it is going through. And a very important tip here is that every time a body tries to move towards the pivot, so whenever the body moves towards the pivot, what it appears to you, if it appears to be clockwise, it is clockwise, and if it appears to be anti-clockwise, it is anti-clockwise.
Okay children, now I have come to you with a setup. This is to understand what all things we have studied so far and also understand one very small concept of couple. Alright, so let us see. In this setup, there is a force which is acting downwards. What is that force? The weight of the cylinder. And there is a force acting upwards also. That's why this body is in equilibrium. What's that force? That force is the force of tension. Alright. Now, we just need to understand that the downward force is equal to the upward force, hence the body is in equilibrium. Look, it is a little shaky because the string is not rigid. It has some elasticity, there is some air around. So just give me a little benefit of doubt and try to understand the concepts in a physical sense. Okay? So there is a downward force and there is an upward force. Both of them are acting at the point, at the pivot point, isn't it? So both of them are not causing any motion. The body is in equilibrium. Now, what if I take this force and I make it act from here? This same force, both of them are in equal magnitude but opposite direction, remember. So what if I take this force and it starts acting in the upward direction? What kind of moment will it cause? It will go towards the pivot. What kind of motion is it? Clockwise. Now, if I take the upward force, this is acting on the same line but it will act in the downward direction. So this is acting in the upward direction, this is acting in the downward direction. In the downward direction also it is causing clockwise motion. In the upward direction this is causing clockwise motion. So together they are causing a complete clockwise motion. So this is causing a clockwise motion, which is a clockwise moment, which will be equal to the force into the distance from the pivot. This is also causing a clockwise motion, which will be equal to the force into the distance from the pivoted point. So together, when two forces which acts about any line, this is a line, two forces which acts about the line in the opposite, on the opposite direction. This is acting upward, this is acting downward, and they have the same magnitude. Let me repeat it once again. Two forces acting in the opposite direction of the fixed pivot of equal magnitude causes clockwise motion, or let's say if this was downwards and this was upward, what kind of motion will it cause? This is causing anti-clockwise motion. This is also causing anti-clockwise motion. So together this upward and downward motion is causing anti-clockwise motion. What will be the magnitude? This force into this distance plus this force into this distance. So two equal and opposite forces about a point which causes the same type of motion, it is called as a couple. In the same line of thought, if there are two forces of equal magnitude acting in the same direction, so if there is one force acting downward from here and one force acting downward from here, are you seeing they are causing different type of motion? This is causing clockwise motion and this is causing anti-clockwise motion. So this clockwise and this anti-clockwise at a point, if they are of equal magnitude, it will balance the scale. A couple will never be able to balance the scale because both of them are causing clockwise or anti-clockwise motion. But if it is not a couple, that means both the forces are acting on the same side. It is both of them are acting downward or both of them are acting upward. So in this case, this is acting downward, this is acting downward. If they can balance each other out like a beam balance, we will say that they can reach a state of equilibrium. Can a couple ever reach a state of equilibrium? No. But two forces on the opposite sides of the pivot in the same direction, downward or upward, alright, they can reach an equilibrium if both the magnitudes match. So remember, two opposite forces acting around the pivot from one downward, one upward can either cause clockwise or anti-clockwise motion. But two forces on the same side, that is both of them are hanging here like a beam balance, it can cause equilibrium if they come to a static point. So children, now that we have learnt about equilibria or equilibrium, we know that equilibrium can be achieved only when there is a clockwise moment as well as anti-clockwise moment, which turns out to be of the same magnitude, so they cancel out each other. So that's a good condition to be for a body or for a system to be in equilibrium. Now we are going to talk about the verification of principle of moments. What is principle of moments? Principle of moments tells us that whenever we have a situation where there are bodies along a line, along a scale, along a meter rule, along a you can say a beam balance, which causes a mix of clockwise and anti-clockwise movements. So it means that it's definitely not a couple. So whenever we have a situation where there are both clockwise and anti-clockwise movements, we can apply the principle of moments. What does principle of moments say? It says that the sum of clockwise moments, if the sum of all clockwise moments, so every force that is causing a clockwise moments, if you add them and if it is equal to the sum of anti-clockwise moments, so all the forces that are causing anti-clockwise moments, if you add them, so clockwise and anti-clockwise added to each other, if they are equal, then the body is in equilibrium. It is not a very confusing concept. Like I have already told you, if in case a body experiences x Newton meter force, x Newton meter moment clockwise, okay, let's say it experiences, let me write it over here, x Newton meter force or moment in the anti-clockwise direction, and if it experiences x Newton meter moment in the clockwise direction also. So what happens over here based on a convention, sign convention? Anti-clockwise moments is positive and clockwise moments is negative. So if both of them are equal and if you add them, what is the total moment? The total moment comes to be 0. So if both the moments are equal to each other and if we add them, then the total sum of moment is going to be 0. So the body is going to be static. It is not going to move. That's what we have studied. So that's exactly what they are trying to say over here. Without the signs, they are saying that if clockwise moments equals anti-clockwise moments, then the body is in a state of equilibrium. Is that alright? So, in case if we have a meter rule which is pivoted, this is how we show a pivot or a fulcrum or a fixed point. It can be anywhere, it doesn't have to be at the center. Okay? So if we have a pivot in hand and if there is a weight hanging, let's say F1 from this side. So how is it going to move? It is going to move in this direction. So this is anti-clockwise, isn't it? Anti-clockwise. And if there is another weight which is F2, this is also going to go towards the pivot. So this motion is going to be clockwise motion. This is clear to all of us. So now let's say this is L1, which is the distance of F1 from the pivot. Remember. And this is L2, which is the distance of F2 from the pivot. So according to our principle of moments, it says that sum of clockwise moments. Who is causing clockwise moments? F2. F2 into L2. That is your clockwise moment in all, because moment is perpendicular distance from the pivot, which is L2, this should be equal to F1, which is causing anti-clockwise moment, sum of all anti-clockwise moments. So F1 into the perpendicular distance, always and always from the fixed point. So if this condition is satisfied, then we can say that the body is in equilibrium. This principle of moments is very important when we have to solve our sums. So whenever they tell us, remember this is a thumb rule, that whenever they tell us that the body is in equilibrium, so where should I, place a certain weight? So in that case, you can directly apply principle of moments. Can you tell me where we cannot ever apply principle of moments? We can never apply principle of moments when we are talking about a couple, because a couple can never reach equilibrium. It will be in a state of constant motion, because a couple or a pair always causes either clockwise motion together or anti-clockwise motion together. So a couple can never experience equilibrium. Equilibrium is only possible when there are two forces which are on the same side. When you see both are acting downwards, or if both are acting upwards, in that case we can always reach equilibrium. Okay children, now we have come with a setup where we are going to verify our principle of moments. Let us verify this. So this meter rod, this is a uniform meter scale that I have in hand. What is a meter scale? Meter scale is a 100 centimeter long foot scale. Alright. So here we have a 100 centimeter long scale. And why do I use the word uniform? Because uniform means the weight or the mass of the scale is uniformly distributed. That means it is not that it's weighing more on this side or weighing less on this side. The density is uniform throughout the scale. So here I have fixed the fulcrum at 50 centimeter mark. So this is my 0 centimeter mark and this is my 100 centimeter marks. Together it makes 1 meter, that is 100 centimeter. Now here I have fixed the fulcrum or the pivot at the center. What happens when I fix the fulcrum or the pivot at the center? That means that the center of mass will be ineffective, because center of mass is also at the center. For a uniform scale, the center of mass is also at the center, which is at the 50 centimeter mark. So remember, whenever the pivot is at the center, the mass of the body which acts downwards, which is the weight. Mass kya hai? Mass, if it is, the mass is 600 grams. So what will be the weight of this body? Can I say 600 GF, 600 gram force? Correct? So 600 gram force is the force acting downwards, but it is ineffective. See, the body is in equilibrium. Can we say this for practical reasons? This is in equilibrium already because the weight over here is equal to the weight over here. So both the weights are equal to each other. Hence, the body is in a state of rest. Now you will say, why is it shaking? Because it's not a stable equilibrium. This wire that I have used has some elasticity. There is some air around. So we cannot expect a completely ideal setup here. But let us try to understand the principle of moments from here. So now I am going to take some identical balls. So this is at 50 centimeter mark. I am going to take two identical balls and I am going to hang it by 10 centimeter mark. This is the 10 centimeter mark. What is happening? It is causing a clockwise movement because there is no weight to balance it over here. Now if I take four identical balls, identical to each other as well as these two balls, and I am hanging it by 70 centimeter mark. Alright, I am hanging it by 70 centimeter mark. Here can you see they have again balanced out each other, isn't it? They have balanced out each other over here in this setup. Look kids, it will not be exactly balanced. There are some things that I have added to it. But could you see that there was a certain moment that was caused on this side, and now it is completely balanced, more or less, for practical purposes and practical understanding. So let me draw a diagram for the setup that I have done just now for you. Okay children, so the setup that we have seen just now, I am going to draw a schematic diagram and I am going to verify the principle of moments for you. That the total anti-clockwise and clockwise are same. That's why the meter rod was balanced. Alright. So this was our setup where we had 0 mark over here, 100 mark over here, and 50 centimeter mark we had the fulcrum. Please draw the fulcrum very clearly because this is where we are going to measure all the distances from. On this side we had 4 balls, 4 identical balls. Each of the balls mass was 6.25. I have measured that for you. And this was at 70 centimeter mark, correct? And on this side at 10 centimeter mark we had 2 balls which are identical to each other as well as these 4 balls. So now let us find by the principle of moments, is the principle of moments verified? So that should mean that the total, what type of moment is this going to cause? It's going to go towards the pivot. What kind of motion is this? This is anti-clockwise movement. What about this? This will also go towards the pivot. So what is the movement over here? This is clockwise. So according to principle of moments, can I say anti-clockwise moments is equal to clockwise moments? Let me write the anti-clockwise under anti-clockwise and clockwise under clockwise. Alright, so what is anti-clockwise moment? Moment is always the force, that is mass. Mass of each ball is 6.25. So what is the force acting on each ball? 6.25 GF. GF is gram force. So the force acting on each gram, because they are falling downwards, they are under the influence of gravity. So whenever mass is given as 10 gram, what is the force acting on it or what is the weight of the body? Don't need to convert it to Newton most of the times. You can just take it as 10 grams. So the force acting on the body or the weight of the body is 10 GF. Or if it is 10 kg, the force acting on the body or the weight of the body is 10 kgf, which is kilogram force. Moving on. So here anti-clockwise moments is going to be force into shortest distance from the pivot or the fixed point. So how much is that? That is 2 into 6.25 GF. That is the force into what is the distance? 50 minus 10. Distance is not 10 centimeter. Distance from the pivot is the difference between them. So that is 50 minus 10 centimeter. This should be equal to the clockwise moments, which is 4 into 6.25 GF into 70 minus 50. So how much is 2 into 6.25? 12.5 GF into 50 minus 10 is 40. This should be equal to, according to principle of moments, this should be equal to, what is 4 into 6.25? 4 into 6.25 is 25. Am I right? Yeah, 25 into 70 minus 50 is 20. What is 12.5 into 40? 12.5 into 40 is 125 into 4. That's what it means. 500 gram per centimeter. And how much is this? 25 into 20. That is also 500 gram per centimeter. So we have verified successfully that if anti-clockwise moment is 500 gram per centimeter, clockwise moment will also be 500 gram per centimeter. Hence they balance each other out and the scale becomes stable. So now I am back with another setup using the same meter scale. However, this time instead of using the center, which is the 50 centimeter mark, I am going to hang it by the 60 centimeter mark. I am hanging it by the 60 centimeter mark. Let's see what happens. So I have hung it by the 60 centimeter mark. This was the center. This was where the center of mass was acting from. This was the center of the meter scale. Now I have set the pivot not at the center but a little askew, which means a little away at 60 centimeter mark. So let's see what happens. It is tilting like this. That means it is having a clockwise moment. Remember, moment should always be calculated in front of you. In front of me, I can see clockwise moment. You might see this as anti-clockwise. but this is clockwise movement. You should always be able to observe the setup in front of you. So this is clockwise. So why did it tilt clockwise? That's the first question that we should ask ourselves. It tilted clockwise because now this side has 40 centimeter and this side has 60 centimeter because this is the 60 centimeter mark. So this part is 6 parts and this is 4 parts of the 10 parts of the scale if I want to make it. So this is a bigger part of a uniform meter rule. So it is going to tilt like this because this is heavier. This has more mass. Since it has more mass, it will apply more force. So force on this side is more than the force on this side. Hence, it's going to tilt on the side of more force. That's what we are going to verify. I have taken the same balls, but now I have taken 24 balls in all. They are all identical and they all weigh 6.25 grams. So I am going to hang it at 100 centimeter mark. This is 60, this is 100, this is 0. So now I have hung these 24 balls from 100 centimeter mark. Can you see now the setup is balanced? The moment I take this off, it gets disbalanced. Correct? But the moment I am hanging it, at 100 centimeter mark, it is getting balanced. Now this is unstable because of the elasticity of the string. But can you see, this is more or less, this is balanced. So I could balance a scale even if it was not pivoted at the center. How could we do that? We could do that based on again the principle of moments. Let us verify this once again. This was the 0 centimeter mark. This was the 100 centimeter mark. Let me write it over here. And this was, let's say, the center, which is 50 centimeter mark. But this is not the pivot. This is the center of gravity or center of mass of this uniform meter scale. What acts from here? The whole mass of the body acts from here. We are coming back to this in a second. Where is my pivot? My pivot is at the 60 centimeter mark. Is this the correct setup? No, I am missing out something. Now over here we have 24 balls. The identical balls, each of which weighed 6.25 grams. Over here, what is acting from here? The moment the pivot shifts from the center, now the mass of the body becomes effective. Earlier when the pivot is at the center, mass is also acting from the center, so they tend to cancel each other out. But now that the pivot is not at the center, it is a little askew, that means it is a little away from the center. That's why the mass of the body will start acting. The mass of this scale is 600 gram. What will be the mass of this setup? It is going to be 24 into 24 is the number of balls into 6.25. Alright. So now let us calculate by the principle of moments. We know that the scale was balanced. So for the scale to be balanced, we know that the total anti-clockwise, it moves towards the pivot. So this is anti-clockwise movement. It should be equal to total clockwise movement. Isn't it? That's all we have to verify. Now let us verify this. So what is the total mass which is causing the total weight or the force which is causing anti-clockwise movement? It is 600 into what is the distance? What is the shortest distance from the pivot or the fulcrum? It is 60 minus 50. This should be equal to what is the total mass of the setup or total weight or the total force of the setup which is causing clockwise movement. It is 24 into 6.25. This is the total weight. And what is the distance or the perpendicular distance from the pivot? It is 100 minus 60. So what do we have here? 600 into 10. This should be equal, ideally, this should be equal to, this is 40. So this is 150, 24 into 6.25 into 40. Alright, so what is 600 into 10? This is 6000 GF centimeter. Please write the units. That should be equal to and is equal to, we can verify that, 150 gram force. This is the total mass of 24 balls and 40 is the distance. This is in centimeter. What is 150 into 40? 15 fours are 60 and 0 GF centimeter. So we can say here also principle of moments is verified. So never should you think that if the pivot is moved, we can never balance the system. If the pivot is moved to one side, wherever the weight is acting from, if the weight of the body or the weight of the scale is causing anti-clockwise movements, then we have to add the weights which causes clockwise movements. I can't add weights over here. So you can't say because the pivot is moving on this side, I will add weights on this side. That's not how you should go about with your problems. You should always check that if certain masses or certain weights are causing clockwise movements, then some weight should also cause anti-clockwise movement. Otherwise, it will never be able to balance each other and we will never reach equilibrium. I hope these two problems have clarified your principle of moments. We will take up more problems and I think this concept should be crystal clear.
Let us go a little into the details of understanding what are the two factors, force and perpendicular distance. How do they affect moment of force and how does it change the type of motion? Let's take an example of a ball. Why am I taking an example of a ball? Because ball undergoes both translational, which is linear, and rotational motion. It undergoes both translational and rotational motion. So you should ask why. Let us see. I have taken into consideration a uniform ball. Again, what does a uniform ball mean? Uniform ball means that the ball has the same density throughout, which means that the density here, number of particles here, is same as the number of particles here, is same as the number of particles here. Alright, that's what we are trying to say here. So can I say that this is the center of the ball? This is not the pivot. I am not saying that I have pivoted the ball at this point. I have not done anything like that. No, this is not what we have done. What I am trying to say is, naturally, this is the center of the ball. Because this is where the center of the mass will act from. All the mass is going to act from this point, this central point. Okay, so this is the natural center of the ball. Alright, okay, moving on. Now, what are the two things that we know about moment of force, which is represented by the letter tau? Remember, so moment of force is equal to the product of the force applied into the perpendicular distance. The perpendicular distance. All words, every single word is important. You have to understand the significance. Why am I saying perpendicular distance? Most kids will, let's say I am applying a force F1. Let's say the radius of the circle or in this case the sphere, the radius of the sphere, let's say it's 5 centimeter. Okay, just taking any random values. I'm applying a force F1 of 10 Newton over here. Now I want to ask you a question, that what will be the torque? What will be the torque? Let us try to identify what will be the torque. Torque is how much? It is the force into perpendicular distance. Let us once again understand what is torque. Let us just quickly recap what is torque. Torque is the turning effect of force. What is it? Turning effect of force. Torque is not just any force. It is a force which leads to the turning effect. That means it leads to the ball to roll. It leads to a certain rotational motion. So we are trying to find out torque due to force F1. So torque due to force F1 should be equal to the magnitude of force F1 into the perpendicular distance of F1 from the natural pivot. Let us call it O. This is what it should be. Correct. Alright. So torque experienced due to force F1 is equal to 10 Newton into how much? What is the perpendicular distance of this force? See, this is a force. Always remember, force is a vector quantity. Force is a vector quantity. So that means that the force is not just going to stay here or here just because I have drawn it like a line like this. No, the force is going to pass through the ball. It's going to affect every part of the ball. It is going to be on a straight line. The force is not going to change its own direction. It will go straight. And this is the point O that we have drawn. Now let us draw it in a magnified manner. Let me magnify it here. I'm just magnifying this part for you. Okay, this part is magnified for you. It's not exactly magnified, but we will see it in a greater detail. So this is the point which is a natural pivot, which means that is the point about which the ball naturally rolls. This is where the force is going from. What is the perpendicular distance of F1 and O? Can you see over here? There is no distance between them. So the distance between O and F, because F is effective like this. So once again, if this is the ball, if this is the force and this is the point of pivot, or this is the point through which, around which the ball rotates, what is the perpendicular distance? There is no perpendicular distance. This is a straight distance over here. The force is acting in this direction. Correct? So the perpendicular distance, and the force will continue to move like this. So the perpendicular distance between this point O and this force F1 is actually 0. So the torque due to F1 is going to be 0 Newton meter or 0 Newton centimeter in this case. Why? Because there is no distance between the point O and F1. There is a distance between point O and F1. That's the question that should arise. This is the distance between F1 and O, isn't it? But what is the context here? The context is torque is equal to the product of force and the perpendicular distance from the pivot. Is there any perpendicular distance of this flat force from the pivot? No. Alright. So in this case, the distance becomes equal to 0 centimeter. So the torque that is experienced when I push the ball, at a point which is collinear, with the pivot. अगर pivot से कोई दो points अगर collinear होते हैं, point A and point B are collinear, then can I say that the perpendicular distance between them is 0? Perpendicular distance between them is 0. Collinear points matlab they fall on the same line. And can you see the line of action of force? What did I say? The line of action of force. This is the line of action of force. The line of action of force and the pivot are actually coincident, or they are collinear. They lie on the same line. If 2 points lie on the same line, what will be the perpendicular distance between them? The perpendicular distance between them is going to be 0. Therefore, the torque experienced is 0. Therefore, in physical sense, what will you observe? In physical sense, you will see that if I exert force, exactly the line of action of force is exactly collinear with the pivot or the natural pivot, the ball will not roll. The ball will experience pure translational motion. It will just move along a straight line. Now this usually does not happen because friction also plays a very important role, and there are many other physical factors which play a role. But if you can do this in a laboratory setup, then we should be able to observe this very clearly. If the force applied on a ball, if the line of action of the force is collinear or on the same line as the pivot, the ball will move straight. it will not show any clockwise or counterclockwise movement. We will not see any of that. I hope the translational motion is clear. Now let us see, how does this same ball experience rotational motion? Why does it rotate? Because here torque is 0. So the turning effect is what we understand. The turning effect is also 0. मतलब बॉल टर्न नहीं होगा, मतलब बॉल रोटेट नहीं होगा, मतलब प्योर ट्रांसलेशनल मोशन है. क्यों ट्रांसलेशनल मोशन है? बिकॉज फोर्स तो एक्ट कर ही रहा है ना बॉडी पे. If force is acting, it will try to cause some motion. Again, we are trying to find what is the torque on this ball due to the force F2. This should be equal to the magnitude of force F2 into the perpendicular distance of F2 from pivot. Now let us see what will be the moment. Let us calculate it now. Can you see what is the perpendicular distance of this force? This is the line of action of F2. So what is the shortest perpendicular distance from the pivot? We had decided that 5 centimeter is the radius of the sphere. Correct? So what is the perpendicular distance of F2 from the sphere? Yes, it is now 5 centimeter. For F1, the perpendicular distance was 0 centimeter because this is where it was along the same line as the pivot. So F2 is leading to a torque. Torque due to F2 is going to be same. Let us take this as 10 Newton only. So 10 into what is the perpendicular distance? 5 centimeter. So what is the torque due to F2? Torque due to F2 is 50 Newton centimeter. Unit is always unit of force into unit of distance. If this would have been 5 meter, then the torque would have been 50 Newton meter, but we have taken it as centimeter. So let's leave it at Newton centimeter for now. Now let us try to understand the direction of torque or direction of moment. You can also say direction of moment. This is important because moments is a vector quantity. Now just imagine this force. Always remember that the force which is acting tries to roll the body. If it has a rolling effect or if it has a turning effect, it will turn always towards the pivot. Turning is always towards the pivot. It will turn towards the pivot. Okay, wherever it may be. So this ball, whenever this force is applied, it is going to turn towards the pivot. So what kind of motion is this? A motion which is something like this. This is along the line of the clock. This is a clockwise motion. Can I say this? Clockwise. This motion is clockwise, correct? So clockwise motion conventionally is taken as negative. So can I say with the sign convention that torque due to F2 is minus 50 Newton centimeter. This tells us that the motion is clockwise. We can also write torque due to F2 is equal to 50 Newton centimeter clockwise. Now let us look at another force. Let us look at a force F3 of the same magnitude. Okay, F3 is of the same magnitude. Now F3 is also not along the line of the pivot. It is not along the pivot. The perpendicular distance of F3 from the pivot is how much? It is also 5 centimeter. But this F3 is going to cause a different type of a motion. I mean that a different direction of motion. What is going to be the direction? F3 is also going to go towards the pivot. So when it is going towards the pivot, what is the type of direction that we have? This is against the clock. So this is counterclockwise, or we say anti-clockwise. So this motion is also anti-clockwise. So let us see what is the torque due to F3. It is going to be the magnitude of F3 into the perpendicular distance from pivot, always from the pivot. Alright, so torque due to F3 is going to be this. Let's say F3 is also 10 Newton. Let us take all of them to be 10 Newton just to be on the safe side, just for the ease of calculation. So this is 10 into what is the perpendicular distance? It is 5 centimeter. So what is going to be the torque due to F3? It will be positive 50 Newton centimeter. which also means torque due to F3 will be equal to 50 Newton centimeter anti-clockwise. Anti-clockwise. Remember, anti-clockwise is always positive. Clockwise is always negative. This is our sign convention, a general sign convention. What if I have a force F4 acting like this? Again, this F force is tangent at this point P. So what is the distance of P from the pivot? It is also 5 centimeter. What about another force? Let's say it is acting like this. F5. What kind of effect will F5 have? This is the point that F5 is tangential at. So this is the perpendicular distance. Tangents are perpendicular to radius. You should know this. You will learn this in your chapter circles. Tangents are perpendicular to radius. Therefore, we are taking the perpendicular distance mathematically. This is also 5 centimeter. Force is 10 Newton. This force is also 10 Newton. So this force F4, so torque due to F4 is going to be clockwise. So it is going to be, can I write minus 10 into 5 Newton centimeter? And torque due to F5, this is your F5. This is causing what kind of motion? Again, this is also causing clockwise. So this will also be minus 50 Newton centimeter. What if I have a force like this? Let's say this is F6. What will be the motion due to F6? Motion due to F6 will be towards the pivot. So this is counterclockwise. So torque due to F6 will be, distance to utna hi hai, perpendicular distance from the pivot, that is 5 centimeter. Isn't it? So this will be, this is in what direction? Again, F6 is counterclockwise. So it will be positive 50 Newton centimeter. I hope the concept of torque is now clear. Okay, children, now we are going to look at some more examples which actually has torque. Here so children, now let us look at a few more daily life examples where we apply the physical quantity torque. We apply the formula of torque and we also apply our principle of moments. Let us see. So children, now that we know what is torque, torque is represented by the Greek letter tau, that is equal to the magnitude of force acting on a body into the perpendicular distance from pivot. Always say it like this. Don't say the distance. Always say the perpendicular distance from the pivot. It always helps. Alright. So let us consider our first example. Here we have a beam balance. In this beam balance, let us take a few figures. So let us say this is 30 centimeter and this is 30 centimeter. Okay. So now I put some weights here. So what is the collective weight that will act downwards? Mass of the whole unit. 1, 2, 3, 4, 5. There are 5 of them. So 5 into 1 kg is the mass of the whole unit. And what is the weight of the whole unit? Weight is a force. Remember, weight, can I write it as? So mass is 5 kg. So weight is 5 kgf simply. Now if you have to convert this to Newton, what is the conversion? 1 kgf is equal to approximately 9.8 Newton. Let's approximately take it as 10 Newton. So the weight of the body is going to be 50 Newton. Alright. Most of the times you don't have to convert. You can just simply take the unit as kgf. Now moving on. Now here I have 5 kg. So 5 kgf is the weight which is acting downwards. This point that we have over here, this is the pivot, isn't it? This is the pivoted point. This is the point about which the two balances A and B are going to rotate. So this is my pivot. I have put a certain weight over here. I don't know the value of this weight. Let's say the value of the weight is X. All right. So now we know that the side A is going to move towards the pivot because there is a weight acting downwards. But this weight, this scale A cannot fall down. It cannot fall down because it is hinged to a pivot. So it is going to move towards the pivot. So what kind of movement is this? This is anti-clockwise. And what about this weight X? This is also going to move towards the pivot. So this is what kind of movement is this? This is along the clock. So this is clockwise. Correct? We don't know the mass over here. All right. So let us apply what is going to be the clockwise motion and the anti-clockwise motion. So for anti-clockwise, we already know the value. For anti-clockwise, the torque, anti-clockwise torque is going to be the total force into the perpendicular distance from the pivot. What is the perpendicular distance from the pivot? The perpendicular distance from the pivot is 30 centimeter. So it is going to be F into 30. Correct? So now the torque which is going to be anti-clockwise is going to be 5 kgf into 30 centimeter. Am I right? So since this is in kgf, let's convert this into meter. So torque is going to be 5 kgf into 0.3 meter. So torque anti-clockwise is going to be 1.5 kgf meter. All right. Now let's come to our part B. Now part B is, the side B is going to have a clockwise movement. You should know this. This is very important, that anti-clockwise is conventionally taken as positive. Clockwise is conventionally taken as negative. So let us see this moment about B. So this is going to go counterclockwise. So torque about B is going to be, this is torque about A. And torque about B is going to be again force that is acting on B. This force tries to pull it downwards, but it is pivoted, so it will move clockwise instead of falling down. Correct? Force into perpendicular distance from pivot. All right. So torque due to B is going to be force. We don't know, that is X kgf into, what is the distance? The distance here also remains 30 centimeter. So this is 30 centimeter. So what is the torque about B? It is X into 0.3 kgf meter. I have just converted 30 centimeter into 0.3 meter. So torque about B is 0.3x kgf meter. All right. So torque about A and torque about B is something that we have already found. If I say the beam is in equilibrium, the beam is in equilibrium. What does it mean? It means that the beam is balanced. That means the total anti-clockwise moment is equal to the total clockwise moment. What type of equilibrium is it? It is static equilibrium, because no body is moving. When a body moves with a constant velocity, it is dynamic equilibrium. But here there is no movement, so it is static equilibrium. So here, if the balance is in static equilibrium, that would mean 1.5 kgf meter is equal to 0.3x kgf meter, because anti-clockwise moment is equal to the clockwise moment, isn't it? That's what it means to be in equilibrium, because we know for the condition for equilibrium is that the algebraic sum of all anti-clockwise moment and clockwise moment are equal. Hence, they cancel out each other. So 1.5 is equal to 0.3x. So can we say 1.5 divided by 0.3 is x? So what is the value of x? 5 kgf. So this simple, very simple experiment tells us that if distance is same from the pivot, then the masses or the weights will also be same. Now a beam balance can come in equilibrium if there is a pivoted point. This is the pivot. This is the pivot that we are talking about. If there is a pivoted point and if there are two weights hanging from the either side in the same direction, can you see? A and B are hanging from the either sides of this pivot, but they are in the same direction, that means both of them are downwards, we can reach a state of equilibrium. Now children, the second example, this is my example 2. The second example that we are taking is that of a steering wheel. Now steering wheel also experiences torque, but here there is a special case. The special case is that of a couple. Let us find out why are we calling this a couple. Okay, so let us say that this is the center of the steering wheel. So this is the pivot. Alright, let's say the diameter is 6 meter. 6 meter is very big. So let us take it as 6 centimeter. Okay, so diameter is 6 centimeter. So what will be the radius? Radius will be 3 centimeter. That's going to be your distance from the pivot, remember. Now let us say we are applying force downwards from here, because when we steer a wheel, both our hands move in the same direction. Both our hands are either counterclockwise or clockwise. Let us see what kind of movement is happening here. So first force, let's say the force is of 10 GF is acting downwards, and this force is also of 10 GF, which is acting upwards. Let us see what kind of moment each of the force is going to cause. So this force is going to move towards the pivot. So what kind of moment is it? The moment is anti-clockwise. What about this force? This force is also going to go towards the pivot. So this is also anti-clockwise. So both the forces are causing anti-clockwise moment. So let me draw a schematic diagram of the steering wheel. So this is the pivot. So let me draw the pivot like this. This is the force of 10 GF. This is the force of 10 GF. This distance is 3 centimeter. This distance is 3 centimeter. Is that correct? This is the schematic diagram. You should always draw this when you are attempting questions based on moment of force. Now, based on the schematic diagram, can you see that there are two equal forces? These two equal forces are in opposite direction. One is downwards, one is upwards. So when in our previous example, both the forces were in the same direction on the either side of the pivot. Here also both the forces are on the either side of the pivot. One is at A and one is at B. But they are opposite to each other. They are working in opposite direction. Hence they end up causing, let us see, A is also moving anti-clockwise and B is also moving anti-clockwise. So together they are causing a complete anti-clockwise motion. There is no clockwise motion or there is no clockwise movement happening here to counterbalance this anti-clockwise motion. So let us see what is going to be the torque experienced by the steering wheel. The torque experienced by the steering wheel is going to be the torque experienced due to A plus the torque experienced due to B. So what is the total torque experienced by the steering wheel? It is going to be the force acting on A into the perpendicular distance of A to P, correct? That is AP, correct? Plus the force experienced at point B into the perpendicular distance of B from the pivot, which is BP. Am I right? So what is the total torque experienced by the body? It is 10 GF, this is force due to A, into 3 plus force due to B is also 10 GF into 3. So total torque experienced by the steering wheel is 30 GF plus 30 GF, that is equal to 60 GF. Please write down the direction anti-clockwise. Now this is a special case. Why is this so special? Because number one, two forces of same magnitude acting in opposite direction. Yes, this is the first observation. What is the second observation? Both forces causes same direction of moment. What is the direction in this example? Anti-clockwise or counterclockwise. This type of force, this type of moment where two equal forces of equal magnitude, we won't say equal forces because we know these forces are equal in magnitude but their directions are opposite. So two forces which has equal magnitude but opposite directions along the same line. What is the same line? AB is the line. This AB is only moving. This AB is the one which is going to move like this, isn't it? So this type of a special torque experienced is called as a couple. Now, there could be certain forces where there is a force acting upward which is of 10 Newton and there is a force acting downward which is of 50 Newton. Here, there is a pivot right in the middle. This is also causing anti-clockwise, this is also causing anti-clockwise, but their magnitudes are different, directions are also different. So we won't call this a couple, but this setup and this setup, they will never achieve equilibrium. You understand why? Because both the forces are causing either clockwise together or anti-clockwise moments together. So they will never be able to reach equilibrium because there is no counterbalancing force here. If one was clockwise, if we had a setup like this, that this is clockwise and this is anti-clockwise, then there is a chance of balancing. But here there is no chance. So couple cannot reach an equilibrium. Remember this. Now children, let us look at another example. So here I have got a setup of a seesaw. Now in this seesaw, there is a boy and there is a girl. So there is Sid and there is Sneha. Okay, so Sid and Sneha are playing on a seesaw. Okay, so in this seesaw, the setup is given to us. So let us quickly draw a schematic diagram. Please do not draw like I have drawn over here. Okay, this is just for your understanding. So always draw a schematic diagram. Do not draw boys, girls. Do not waste your time doing that. There is no marks for that. Just laughs. All right. So here we have a pivot. Here we have Sid. Acha. Sid's weight is going to act downwards, na? Right? And what about Sneha? Sneha's weight is also going to act downwards. Correct? So how much weight is going to act from Sneha? It will be 25 kgf. How much weight is going to act for Sid? It is going to be 30 kgf. What is the distance of Sid? Where is he sitting? 5 meter from the fulcrum or the pivot, right? And where is Sneha sitting? 10 meters from the pivot. All right, so let's say this is point A, this is point B, and this is point. Question that we are asking here is, which side will the seesaw tilt? Okay, which side will go down? Will Sneha move down or will Sid move down? Now here, don't be very quick to answer that obviously Sid's weight is more, so Sid will go down. No, for moment or for rotation about a fixed axis to happen, you have to take the product. You have to take the product of force and perpendicular distance. So you can't directly by looking at the force, you cannot say which side it's going to tilt. You can say it if the distances are same or constant. Here distance is not same. So we have to calculate. Let us see. Sid is going to definitely not falling down. Sid is going to go counterclockwise. And what about Sneha? Sneha is also going to move towards the pivot. So she is going to go clockwise. Let us try to calculate separately what is going to be my clockwise moment and what is going to be my anti-clockwise moment. So torque due to A, this is A, this is Sid, is going to be force of A, that is how much I am directly writing, 30 kgf into, what is the distance? 5 meter. Now this is anti-clockwise, so torque due to A is going to be 150 kgf meter. Please write the direction. It is going to be anti-clockwise. Let us calculate the torque due to B, which is torque due to Sneha. What is her weight? Which is the force? That is 25 kgf into what is the distance? 10 meter. So what is the torque due to Sneha? It is 250 kgf. What is the direction? Sneha is moving clockwise, isn't it? She is moving towards the pivot. It is in the direction of the clock. So it is clockwise. Now look at this. What is the total anti-clockwise moment? It is 150 kgf meter. What is the total clockwise moment, it is 250 kgf meter. So which side will go down? Who will go down? It is going to be Sneha, because Sneha has 250 kgf torque. That is more than 150 kgf, isn't it? And by how much? What is going to be the net torque? What is the net moment, or we can say what is the net torque? Net torque is the difference between both the torques, because Neha can go down with the entire torque of 250 kgf, because there is Sid sitting over here who is offering a counterbalancing of 150 kgf. So what will be the net moment? It will be 250 minus 150, that is equal to how much? 100 kgf. And what is the direction? It will go clockwise. All right. So based on these examples of where situation of equilibrium can be reached, where situation of equilibrium cannot be reached, here we can reach equilibrium. I'm going to change this question a little bit for you, and let us see how can we reach equilibrium in this situation of Sid and Sneha on a seesaw. Let's say there is a third person C, Ashima. Now Ashima is here to bring about equilibrium. Where should Ashima sit to balance the seesaw? So let's say Ashima weighs 15 kg. Okay, Ashima weighs 15 kg. Where should C, let's say, sit for balance, so that the whole setup is in balance? So both of them are floating in air. In fact, all three of them can float in that seesaw. Where should Ashima sit? That question can be answered very easily, because she has to sit on the side of Sid, because Sid is the one which has lesser torque, isn't it? Very easy. But please don't write that and come for your physics exam. You have to give her exact position, exact distance from the pivot. Remember this. Please don't just write she should sit on the side of Sid. That is not a correct, or that's not a complete answer. You need values. Whenever they ask you where, when, you need numerical values to it. So let us see, where should a person C weighing 15 kg sit for balance? Ashima, we have already figured out that Ashima has to sit over here. That's for sure, because it's Sid who is up now. So we have to add weight on Sid's side. So Ashima is now sitting over here. So Ashima's weight is 15 kg. Ashima is person C. So Ashima is going to cause what kind of movement? She is going to cause anti-clockwise movement. All right. So let us see where she is going to sit for equilibrium. Let us draw the schematic diagram. This is the pivot center point. This is a distance of 5 meter. This is where A is sitting, correct? Whose weight is 30 kg. Ashima will sit somewhere over here. Ashima will sit somewhere over here. Her weight is 15 kg. Why? Because this is causing anti-clockwise movement, and sitting over here at a distance of 10 meter from the pivot was Sneha, who was causing a huge clockwise movement even though her weight was less. Isn't it? Because she was at a farther distance from the pivot. So clockwise was greater than anti-clockwise. Therefore, whenever we have to balance it, whenever balancing is required, we have to add more weight here so that it becomes equal. So that's why Ashima is sitting over here. So A is sitting over here, B is sitting over here, and C is sitting over here. Now these two weights together, A and C, are going to cause what kind of movement? Anti-clockwise movement. Let us calculate. Torque due to A plus torque due to C is equal to 30 into 5, 30 into perpendicular distance of A from pivot, plus 15 into X, that is the perpendicular distance of C from the pivot, because we have to find where she is sitting. That means at how much distance from the pivot she is sitting. And what about this is going to be anti-clockwise? What about clockwise? Torque which is caused by B, this is going to be anti-clockwise. This is going to be clockwise. So this is how much? This is 25 into distance, perpendicular distance, that is 250. This is clockwise moment. So now we said that the balance, or the seesaw over here is going to be balanced. If the seesaw is balanced, that means we have reached a state of equilibrium. Am I right? We have reached a state of equilibrium. What does that mean? That means that total clockwise moment should be equal to total anti-clockwise moment. This is also called as principle of moments. For a body to be balanced, the total clockwise moment is equal to the total anti-clockwise moment. Remember this. So what is the total clockwise moment? 30 into 5. Total clockwise moment is 250 is equal to, don't need to write units all the time, but I tend to write it because in the end, you just go and write the numerical value. Then the teacher is not going to give you any mark. In ICSE, you will get 0 marks if you write just numerical value. Correct numerical value without unit carries 0 marks. All right, remember this. So writing units is as important as finding your answer. So 250 is your total clockwise movement. तो लिख ही देते हैं. Let's be on the safe side. kg meter is equal to total anti-clockwise. कितना है total anti-clockwise? Total anti-clockwise, yeah. Total anti-clockwise is 30 into 5, that is 150 kg meter plus 15x kg meter. यही है कि नहीं? और हमें बोला गया है that now the beam has to be balanced. The seesaw has to be balanced. Therefore, these are equal to each other. So, 250 minus 150 is equal to 15x. So, 100 is equal to 15x. So, what should be the distance x? It should be 100 upon 15. And what is 100 upon 15? 5 3s are 15, 5 20s are, 3 1s are, 3 6s are 18, 3 6s are 18, 6s are 18. It can continue forever. So 6.66 meter will be the distance. We are finding the distance. So at what distance should Ashima sit? For the seesaws to be balanced, she should sit at a distance of 6.66, or you can say approximately 6.67 meter from the pivot. What if they ask you at what distance she is sitting from SID? She is sitting at a distance of, SID is at a distance of 5. This distance is 5 for SID. Ashima is sitting somewhere over here, isn't it? Ashima is sitting here because she is at a distance of 6.67 from the pivot. So how far is she from SID? She is at a distance of 1.67 from SID. So your calculations depend, or actually your accuracy of calculation completely depends on how well you can draw your schematic diagram.